A Taylor series only works smoothly everywhere near a point. A Laurent series is built specifically to handle a point where things break down, allowing negative powers to appear alongside the usual positive ones. Pattern to recognize. Laurent series are valid inside an annulus, a ring-shaped region between two circles, not inside a solid disk like a Taylor series. The general form is f of z equals the sum from n equals negative infinity to infinity of a sub n times, open bracket, z minus z naught, close bracket, to the n. This is valid for r less than the magnitude of z minus z naught less than r, an annulus. Pattern to recognize. Look at how far the negative powers extend in the Laurent series, and that tells you exactly what kind of singularity you're facing. If there are no negative powers at all, it isn't really a singularity, it's removable, meaning the function is secretly fine there. If there are finitely many negative powers stopping at some highest one, it's a pole, and the highest negative power tells you the order. If the negative powers never stop, infinitely many of them, it's an essential singularity, the wildest and least predictable type. Worked example. Classify the singularity of f of z equals, open bracket, 1 minus cosine z, close bracket, over z cubed at z equals 0. Step 1. Expand cosine z. Cosine z equals 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus more terms. Step 2. Find 1 minus cosine z. This equals z squared over 2 factorial minus z to the 4th over 4 factorial plus more terms. Step 3. Divide by z cubed. F of z equals, open bracket, z squared over 2 minus z to the 4th over 24 plus more terms, close bracket, over z cubed, which equals 1 over 2z minus z over 24 plus more terms. Step 4. Classify. Only one negative power, 1 over z, appears, so this is a pole of order 1. Now, separately picture a giant semicircle sitting on the real number line, its curved edge arching up through the complex plane. This is the semicircle trick. Pattern to recognize. Split the closed loop into the straight real axis piece, which is what you actually want, and the curved arc piece, which usually vanishes as the radius grows infinitely large, provable using the ML inequality. Set up the closed loop integral over c sub r of f of z dz equals the integral from negative r to r of f of x dx plus the integral over the arc c prime sub r of f of z dz. As r approaches infinity, if the arc integral approaches 0, shown via the ML inequality, then the integral from negative infinity to infinity of f of x dx equals 2 pi I times the sum of residues at the poles in the upper half plane. Worked example. Evaluate the integral from negative infinity to infinity of 1 over, open bracket, x squared plus 9, close bracket, dx. Step 1. Find the poles. Z squared equals negative 9, so Z equals plus or minus 3i. Step 2. Only 3i lies in the upper half plane. Step 3. Find the residue. The residue at 3i is the limit, as Z approaches 3i of, open bracket, Z minus 3i, close bracket, over, open bracket, Z minus 3i, close bracket, times, open bracket, Z plus 3i, close bracket, which simplifies to 1 over 6i. Step 4. Apply the theorem. The integral equals 2 pi I times 1 over 6i, which equals pi over 3. Now, pattern to recognize. Whenever an integral runs from 0 to 2 pi and only involves cosine and sine of theta, substitute z equals e to the I theta, converting the whole thing into a closed loop integral around the unit circle. The substitutions are z equals e to the I theta, cosine theta equals, open bracket, z plus z to the minus 1, close bracket, over 2. Sine theta equals, open bracket, z minus z to the minus 1, close bracket, over 2i, and d theta equals dz over iz. Worked example. Evaluate the integral from 0 to 2p of d theta over, open bracket, 2 plus sine theta, close bracket. Step 1. Substitute z equals e to the I theta. So sin theta equals, open bracket, z minus z to the minus 1, close bracket, over 2i, and d theta equals dz over iz. Step 2. Rewrite as a closed loop integral. This becomes the closed loop integral over c of 1 over iz times 1 over, open bracket, 2 plus, open bracket, z minus z to the minus 1, close bracket, over 2i, close bracket, dz. Step 3. Simplify the denominator. 2 plus, open bracket, z minus 1 over z, close bracket, over 2i, equals, open bracket, 4is plus z squared minus 1, close bracket, over 2is. Step 4. Combine everything. The closed loop integral becomes the closed loop integral over c of 2 over, open bracket, z squared plus 4i's minus 1, close bracket, dz. Step 5. Find the poles using the quadratic formula. Z equals, open bracket, negative 4i plus or minus the square root of, open bracket, negative 16 plus 4, close bracket, over 2, which simplifies to negative 2i plus or minus I root 3. Step 6. Check which pole lies inside the unit circle. One pole is at I times, open bracket, root 3 minus 2, close bracket, approximately I times negative 0.27 with magnitude approximately 0.27, which is inside. The other pole has magnitude approximately 3.73, which is outside. Step 7. Find the residue at the inside pole and multiply by 2 pi I. The residue at the inside pole is negative I root 3 over 3, and 2 pi I times this residue gives exactly 2 pi over root 3, which equals 2 root 3 pi over 3, matching the standard formula and confirmed by direct numerical integration.